All right, welcome to The Explainer. Today, we're going to tackle a really fundamental question in AI. How do these super complex models actually learn anything? It's not magic. It's a fascinating process of search and optimization, all happening on a scale that's almost impossible to imagine.
So picture this. You've got a database with trillions of records, and there's no index. Your job is to find the single best one. That's kind of what it's like training an AI model. So the real question is, how do you even begin to frame a search problem that massive in a way a computer can understand and solve? Well, we do it using something called a loss function. The easiest way to think about it is to imagine a huge, hilly landscape. The higher up you are on a hill, the more wrong your model's predictions are. And the low spots, the valleys, that's where your model is getting things right. So the mission is pretty simple. Find the absolute lowest point in that entire landscape. Okay, so we have this landscape, right? Our goal is to find the bottom. But how do we actually do that? We've got the map, this loss function, but what's our navigation strategy? How do we find our way down? Well, you start with the most intuitive thing you can think of. You just walk downhill. From wherever you are, you find the steepest path down and you take a step. This whole process, this step-by-step walk, is called gradient descent. It's a really careful, methodical way to get to the bottom. But here's the catch. What happens when this landscape isn't just a few hills, but a massive, continent-sized mountain range representing a huge data set with millions or even billions of points? Yeah, that's where we hit a major snag. To figure out the true steepest direction, you'd have to look at every single piece of data for every single step you take. That's not just slow, it's basically impossible. It's like trying to survey an entire continent just to decide where to put your foot next. It's just not going to happen. And this is where a really clever shortcut comes in called stochastic gradient descent, or SGD for short. Instead of looking at the entire landscape, you just take a quick peek at a small, random sample of the data, we call it a mini batch, to get a pretty good guess of which way is down. Then you take a step, and you do it all over again. So let's break down the trade-off here. Full gradient descent is slow but steady. SGD is way faster, but its path is, well, it's pretty noisy and all over the place. But here's the really cool part. That randomness can actually be a good thing. It can help the model jump out of these little shallow valleys where the slower, more careful method might just get stuck. Okay, but let's be honest. That zigzag path looks kind of inefficient, doesn't it? It feels like we're wasting a lot of energy bouncing back and forth. So, are there better tools? Can we get the speed of SGD, but make the journey a little bit smoother? You bet there are. And the first big idea is something called momentum. It's a really simple but powerful concept. Basically, it helps our little downhill walker remember the direction it was just going, and it encourages it to keep moving in that same general direction. Think of it like giving a heavy bowling ball a push downhill. It's going to build up momentum, right? It'll smooth out the ride, roll right over the little bumps, and just get to the bottom a whole lot faster and more directly. It stops all that useless side-to-side wiggling. So, momentum is a fantastic tool, a huge step up. But in deep learning, we're always trying to do better. So, can we do even better? What's the state of the art? Is there an optimizer that combines all these good ideas into one super navigator? There is, and it's called Atom. Honestly, for a lot of deep learning problems, Atom is the go-to optimizer, and here's why. It uses momentum to smooth out the path, and it does something else really smart. It adapts the step size for every single parameter in the model. It's like a seasoned hiker who knows to take big, confident strides on flat ground, but tiny, careful steps when the terrain gets steep and tricky. Okay, so we've got these amazing tools, right? SGD, Momentum, Atom, they're all designed to find the bottom of the valley. But what if we've been asking the wrong question this whole time? Is the first low point we find always the best one? And that, right there, is a huge question in deep learning. Because the truth is, these landscapes are almost never a simple, perfect bowl. They're what we call non-convex, which is a fancy way of saying they are full of traps, dead ends, and deceptive valleys. And this is where the real challenge comes in. You see, our optimizer might find what's called a local minimum, a little dip that looks like the bottom and just stop there, completely missing the true global minimum, which is way lower in a totally different part of the landscape. Or even worse, it could land on a saddle point, which is this weird, tricky spot that's flat in some directions, but not in others. It's a really easy place to get stuck and stop making progress.
What this all means is that picking the right optimizer and tuning its settings is often more of an art than an exact science. It's not just about having the map, it's about being a skilled navigator on this incredibly complex and sometimes deceptive terrain.
So, we hope this little tour through the world of optimization has helped clear things up. If it did, and you enjoyed the journey, we'd really appreciate it if you'd like, share, and subscribe for more deep dives just like this one.
And we'll leave you with one final question to think about. If our optimizers are this smart, and getting smarter all the time, why do some AI models still completely fail to learn? What other hidden challenges are lurking in these massive digital landscapes?